Well, hello, everyone. This is Betty Hurley-Dasgupta, and I'm here with Carol Yeager. We're both facilitators of Vizmath, a MOOC, actually a CMOOC, and we welcome you to this session. Just a few brief announcements. Be sure to use Twitter to share what you've learned, and all you need to do on Twitter is do #Vizmath. Also, please consider subscribing your blog to the Vizmath site so that we can have more sharing among each other. And there is also a Facebook group called Vizmath: a CMOOC. So we'd love to see you there. That was begun by one of the participants. So I'm very happy today to have Rachel Thomas and Marian Freiberger from PLOS Magazine, who are going to talk about the magazine and also talk about Symmetry. So welcome both.
Hi everyone. Just to show that I'm a real person, I'm Rachel. I'm sitting in Marianne's kitchen. We're really pleased to be a part of this Vizmath course, so thank you very much, Betty and Carol, for running the course and asking us to contribute to it. So Vizmath is described as a place where the beauty of maths is celebrated. Oh, I just want to apologize at the start that we will continue to say maths with an S because that's what we say. So I apologize because I know it will sound strange to your ears. So I'll just get that out of the way at front. As I was saying, so Vizmath is a place where beauty of maths is celebrated, and that's something that we do on PLOS all the time, every day. Hi, John. You can see on the slide that you've got in front of you a couple of pictures. I'm the one at the top, and Marianne, who's sitting across from me on the table, is the picture below. And you can also see a screenshot of our website, PLOS Magazine. I'm going to see if this tour works. I'm going to take us onto PLOS, so let me know if this works. So hopefully you should all be seeing PLOS Magazine now on the whiteboard space. Can everyone see that? Great, I think you can see that then. So this is our website, PLOS Magazine. We've been going for 15 years now, so one of the earlier science websites and online magazines. The whole point of PLOS is to try and open a door onto the world of maths for the general public. So we want people to be able to not just sort of have a glimpse of mathematics, but actually walk into the world of maths and get a real sense for what mathematics is, what it can do, and have a sense of the appreciation that mathematicians have when they look at the world. So to do that, we have a number of sort of types of content that we produce. One of them is the news stories we produce, which I'm showing you now, which is maths behind current events or new mathematical research. So these are our latest 4 news stories. And How to Make a Marriage Stable and a Nobel Prize for Quantum Optics. They're both the mathematics of 2 of the Nobel Prizes, the Economics Nobel Prize and the Physics Nobel Prize. And then also the fractal photophysics finish is an example of some new maths research that has been done. So our news is trying to reveal the maths behind stories you might have seen in the press or current events that you just might not realize have got a really mathematical angle. We also produce sort of in-depth articles. Here's an example of the last 4 that we've done. The first 2 you can see on the screen about ESP and Bayes and significance are some research that's been done into understanding the validity of claims about whether people have extrasensory perception and the use of statistics and probability theory to understand that. Understand the Unseen is this great article about some numerical techniques that were vital in early NASA flights to the moon. And the Palooza Climb and the Story of a Fifth Dimension is one of a pair of articles we produced recently with an interview with a theoretical physicist about how many dimensions there are in the world that we live in. So the kind of content we cover in our articles is anything and everything. Basically, if you tell us a type of content, if you tell us something you're interested in, I can bet you we will find a mathematical angle to talk about that. We cover art, we cover politics, we cover all the areas of science, and there's pretty much always a mathematical angle to it, and that's what we try and cover in an in-depth article. The other main point of what we do on PLUS is to try and represent the human side of mathematics, because mathematics is often seen as this solid stone edifice that has existed since the dawn of time, where actually what mathematics is this dynamic and incredibly creative area of research, area of knowledge that's constantly being contributed to by really passionate, creative people. And that's not really the picture that most people have of mathematicians. So one of the things that we try to do on PLUS is show the stories behind the maths and show stories about the people who produce the mathematics. So one of the ways we do this is we have regular career interviews. I'll show you some of them. We have career interviews with people who use mathematics in their career. So some recent examples are Marianne went to Krakow for a conference and met the president of the European Mathematical Society, Marta Sansole, and she's had a fascinating career. We've got a biomedical engineer in Africa, Tanya Morton, who works for a software company called MathWorks, who works on really interesting applications of mathematics. So we try and cover a real range of ways that mathematics might be used in people's jobs, not necessarily academic jobs in any way, but jobs that have some kind of mathematical component to them, to try and show the breadth of ways you could use it. And the other way we try and present the people behind the mathematics is we produce podcasts, which is, there's nothing better really than hearing a mathematician talking about their research and the excitement and the passion they have for the work they do. It's fantastic, and it's something sadly that most people don't get to hear. They don't get to hear about the mathematics from the people who actually do it day to day. So that's been a really exciting thing that I've been able to be a part of, is when we interview people, such as interviewing this theoretical physicist David Berman about dimensions, recording that, and when you hear how he speaks about his work, it's just, you get a whole new way into the subject really, and you get an appreciation for how he feels and his enthusiasm for the subject area. So that's pretty much everything to do with PLUS. We have some puzzles, we have book reviews of recent books, I'll show you. We've met posters, but basically that's the kind of content we produce here on PLUS. We're based in the Centre for Mathematical Sciences in Cambridge University in England, and we're part of a larger organisation called the Millennium Mathematics Project, which is a national initiative which aims to promote mathematics to the wider community. And we have a number of ways of doing that, working with teachers, with students, face-to-face and online, with public lectures. And PLUS magazine is part of that. It's our magazine for the general public. And so I don't know if anyone has any questions about PLUS that they want to ask now. I'll just check whether anyone has got anything they wanted to ask us about that.
This is Betty. I was just reading the super cooperators thing. Could you just give us a couple of sentences on that, how they use math to show cooperation in the world?
Oh, that was fantastic. It's a really good question. Martin Novak, the author of that book, along with Roger Highfield, the journalist, And Martin Novak's based in Harvard. And I was lucky enough to go and interview him earlier this year, and it's absolutely fascinating what they do. Some of you may have heard of something called the prisoner's dilemma, which is a situation where two people are in a kind of a game situation where they both have to make a decision to either, well, it's called defect or cooperate. So they either, if you think of two people who committed a crime and they're being interviewed by the police, and if one of them, they're being interviewed separately in different rooms, so they don't know what the other person is saying, and if one of them, if they both deny that they've been involved, so they're cooperating with each other, then they'll both get really long jail terms. If they both, I've got to make sure I get this right around, if they both admit that they've been involved, then they'll get a shorter jail term. In fact, they'll get the shortest jail term if they don't. Have I done it the right way around? Anyway, I might have this slightly wrong. But if one jobs in the other, jobs in is an English thing. If one says that they did it and says that the other person was involved, then they'll get an even worse, one will get a better jail term than the other. So basically you've got the situation where you're both trying to make a decision about a course of action, but the payoff you get depends on the kind of behaviour you have. And this is called prisoner's dilemma, and it's a standard thing that's used throughout economics. And what they've done, Martin Novak and people in his group, is they've combined that with some evolutionary ideas, things to do with mutation and natural selection. And by describing those things in a mathematical way and combining it with this idea of the prisoner's dilemma, they've developed what they call evolutionary game theory. And if you run these mathematical simulations of evolutionary game theory, in all sorts of situations, all sorts of different kind of setups that you could set these games up to run, almost always cooperating comes out as the best possible outcome for the population, whereas for individuals, being mean and kind of thinking only of themselves, that wouldn't be the best option. But actually, when you play it as a population, over and over again, cooperation becomes this, the best strategy for surviving for the population. And so it's just this interesting mathematical argument for why altruism may have evolved and may have become a natural thing that humans do. And also it's a kind of altruism that they have models where it's clearly mimicking patterns of behavior that you see in the animal world. So it's just a really interesting idea of this quite mathematical idea and this quite mathematical setup that ends up giving you a really interesting insight into something you wouldn't think has a mathematical basis at all.
That's great, thanks. There's a note from Carol, but it's a comment, so I don't think we have any other questions, but that's great.
I have one question, and I wanted to ask Marianne and Rachel if perhaps you have any numbers on how many, not so much students, but how many classes and schools use PLOS Magazine as either part of their curriculum or as an added plus for the students. Do you know that sort of thing?
We don't have a really clear data on that because the online web stats are hard to monitor exactly who's using it, but we do know that the take-up of our hard copy material is really strong in schools. So we send out stuff. There's about 6,000 secondary schools. We're really aiming for the higher secondary, so 15-year-olds and above, and we mail out posters and postcards and things like that to all secondary schools in the UK. And as far as them being used, I mean, they are becoming more and more prominent. But what's interesting is that we had some posters, had a push for our posters, and all of a sudden they must have got discovered by some stream of teachers, both here and internationally, because we started getting about 1,000 poster requests a day, and actually had to shut down the poster requests because we didn't have the manpower to send all these posters out anymore. So it's hard to know exactly how many people are using the online material, though we get really good feedback in a kind of ad hoc way from teachers. But we get certainly a lot of requests from the hard copy material. That gives us a better chance to monitor exactly who's using it. Okay, if there's no more questions, shall I move on to the next to the topic of symmetry? Okay, so I'll take us back to our slides. Okay, so what Marianne and I thought we would talk about is a part of mathematics that both of us find particularly beautiful, which is symmetry, and we find the mathematics behind symmetry really beautiful and fascinating. But what's really nice about this topic is symmetry is something that everyone finds beautiful, whether you're mathematically inclined or not. So humans have a sort of innate appreciation of symmetry. It's sort of a sort of well-known fact that often the most beautiful faces are the ones that are symmetric. We're often very attracted to symmetry that we find in nature, in the symmetry of flowers, the symmetry of plants, and you see a really nice picture here of the symmetry you can see in butterfly wings, the symmetry you can see in reflection of a lake. There's lots of theories why we have this innate appreciation of symmetry. One of them is that, particularly in the animal kingdom, that symmetry is an indication of good health and good fitness. So perhaps that's why we have this appreciation of symmetry. But the other way we appreciate it sometimes is we're actually drawn to striking examples where the symmetry breaks, so where there's something asymmetric. So often in art, the things that really catch your eye are where the symmetry is broken. In the same way, you know, some of the decorative patterns that are used throughout the world are actually highly symmetric. So we have this appreciation for both when symmetry is present and when it's absent. Even though we might not be using a mathematical way to think about it, we have this sort of intuitive response to what symmetry is. And this isn't a new thing. This has been something that's been going on for millennia for humanity. The picture you can see at the top of the screen here on the black background are these Neolithic stone balls that were carved in Scotland about 3,000 years ago. I've seen one in the flesh in the Ashmolean Museum in Oxford, and they're beautiful things. They're incredibly tactile to look at. Unfortunately, obviously, I'm not allowed to touch them. They're so intricately and carefully carved. And this, this is 3,000 years ago. This is stone tool. This isn't using, metal and things. This is using stone tools to carve. And they're so beautifully carved and so carefully carved. And more than half of them, which is, I think it's about 800 of them, are carved. They're all carved with, most of them are carved with evenly spaced kind of knobs. You can see this one up here. You can see sort of a nodule on the sides, and this one's got a lot more evenly spaced knobs. So most of them are carved in that way, but over half of them, so about 800 of them, remarkably are carved with either 4, 6 or 8 symmetrically placed knobs. So even though this is 3,000 years ago, more than a millennia before the Greeks discovered the Platonic solids, which you can see down the bottom, this row along here, you've got the thing called the Platonic solids, which are, there's the tetrahedron, there's a cube, there's something called an octahedron, a dodecahedron, icosahedron. More than 1,000 years before these were discovered by people interested in mathematics, humans were finding them in an intuitive, sort of exploratory way in these Neolithic carved stone balls. So it's amazing that we've had this appreciation of symmetry for so many years, right from we sort of observed the world, really. So I think now I've got one more slide. And just another couple of examples of really beautiful symmetry that people have produced and that you can see. One is these beautiful floor tiles in San Marco's Basilica in Venice, which is from the 13th century. So it's amazingly beautiful to still be able to see these from such a long time ago. But you can see within the patterns, in the tiling of specific panels, and also in the overall design of that picture, they're really using symmetry as a way to hold the composition together. And this incredibly beautiful picture you can see on the black background on the right is a mathematical object called E8. I won't go into the details of this object except to say that it's associated with an object, the symmetries of an object in 57-dimensional space, so which is why I'm not going to go into the details of it because I don't really understand it entirely myself. But by approaching symmetry from a mathematical viewpoint is something that is a prime concern to a lot of mathematicians. It's an area of active mathematical research, and it's incredibly beautiful, and it produces amazing. A mathematician's approach to understanding symmetry and studying symmetry also produces these incredibly beautiful objects. So now I'm going to hand over to Marianne, who will carry on telling us about symmetry.
Hello everybody. I'm switching the video on for a minute so you can see me, hopefully. Hello. Okay, so we've now seen all these examples of symmetry explored in art, but also in mathematics, and also quite intuitively by people. So let's move on and think about what symmetry really is. So we know exactly what we mean by symmetry. When we see a symmetrical object, we can spot immediately that it is symmetrical. But what is a symmetry really? So the first thing to understand or to think about really is that in mathematics at least we think of symmetry as an action, as something that we can do to a shape. And we say that it's like we look at something as a symmetry if it leaves something unchanged. Okay? So on this slide here we have the example of a square, and you can the square has several symmetry axes that you can reflect it in, and it will look exactly the same after you have reflected it. So there's 4 symmetry axes. It's the 2 diagonals, a vertical and a horizontal axis. And if you reflect within these axes, the picture you get afterwards is exactly the same as when you started. And also, another thing we can do to the square is to rotate it around its center point through either 90 degrees, or 2 times 90 degrees, that's 180 degrees, or 3 times 90 degrees, that's 270 degrees. So all of these actions, the 4 reflections and the rotations, is what mathematicians call symmetry. So it's an operation, it's an action that you can do to a shape. And you can ask yourself about what kind of symmetries all sorts of shapes have. So for example, if I go to my next slide, I have a triangle. And as you can see here, in this case, there are 3 symmetry axes in the triangle. I've labeled them A, B, and C here. And you can also, there's also 2 rotations around about the center of the triangle through a third of a full turn. So that's 120 degrees and 240 degrees. So the 3 reflections and the 2 rotations leave the triangle unchanged. So in mathematical terms, that's what symmetries are. They are transformations of shapes that leave them unchanged. So far, does anybody have any questions? Does everybody understand what a symmetry is? Okay, well, that looks pretty good. It looks like you're all following me so far. So let's think a little bit further and see what happens when you combine symmetry. So let's stay with the triangle. And suppose that I first reflect the triangle in its central axis the one that goes vertically down. So if I do that, let's see if I can use the little pointer. I'm not sure if that's where, oh, can you see my pointer moving? No. Can you see it moving now? Yeah, okay. So I reflect the triangle in this axis. So what happens is that this point at the top stays where it is, and this one just gets sent over there. These two get exchanged. It's like the vertical axis is like a mirror, basically. Okay, so now suppose I follow this by a reflection in this diagonal axis here. So this point that lies on the axis, point B, stays where it is, and these two get interchanged again. Okay, so if I see what happened to the three corners of the triangle, where they end up, we've got A, B, C in that order. Now, if you think about it, that's exactly what you'd get if you just rotated the triangle around through 120 degrees. Okay, if I rotated this triangle through 120 degrees around its center point, A would go here, B would go here, and C would go here. Okay. So what we've just shown is that the two reflections, when we combine them, when we do one after the other, give us a rotation. Okay? And, well, in some sense, this is reasonably intuitive, because since the symmetry is something that leaves something unchanged, if I combine two things that leave something unchanged, together they will also leave it unchanged. So therefore, any combination of two symmetries is going to be another symmetry. Okay? The question is, which one? So here I've combined two reflections, and it wasn't that obvious to see that the two reflections would give me particularly this rotation. But what I know for sure is that combined they will always give me another symmetry. Okay, so what does that tell us? That tells us that we can understand the symmetries of a shape, like a triangle, by seeing how they combine and how they interact. So if I go to my next slide. Now, this table might look a bit frightening, but don't be frightened of it, because all it tells you is how the different symmetries of a triangle combine. Okay? So you don't have to go into this table too much, but just imagine that one of our reflections was labeled A, okay? Another one was labeled B, and this table just tells me that if I first do A, and then I follow it by B, what I end up with is rotation 1. So if I label my two rotations, rotation 1 and rotation 2, then this table tells me exactly what happens when I first start with reflection A and then I do reflection B. Okay? In a similar way, I can find out what happens if I first do rotation 1 and then follow it by reflection C. So this table basically tells us pretty much everything there is to know about the symmetries of a triangle. It tells us what the symmetries are. So we've got 3 reflections and 2 rotations, and it tells us how they combine. Okay? And there's something I should say, that we always include doing nothing as a symmetry, because it also leaves an object unchanged. And we also, in order not to get confused about clockwise and anti-clockwise rotations, for example, we just take note of the fact that, maybe if I go back, that rotating clockwise through 120 degrees is the same as rotating anti-clockwise through 240 degrees. So just in order to not to get confused, we can consider these two the same. So we don't really need to distinguish between clockwise and anti-clockwise, basically. So this table tells me everything there is to know about the symmetries of a triangle. And actually, this table, what it is mathematically, is what mathematicians call a group. It's a representation of a group. And a group is, well, it's just a self-contained system of symmetry of an object. Okay? Now, group theory is a massive area in mathematics. It's been around since the times of Galois. Yeah, I'll get there in a minute. So it's a huge area in mathematics that has led to, I don't know, it's probably one of the biggest fields in mathematics. And it was only really understood in the beginning of the 20th century, no, I think it was the 19th century, by this person whose picture you can see here, Évariste Galois. He was the first person to really get his head not around the fact that there are symmetries, because even the ancient Greeks already knew that, But the fact that we can see that we can encode the symmetries of an object with such a table here, which is mathematically a group. Now, unfortunately, Galois died very, very young in a duel, which nobody's really quite sure why, but it's said to involve a woman. And in the last night before he had to go out and fight the duel and eventually die, he was writing up his mathematical papers, and in these papers I think he first came up with the word group for these symmetry patterns that he found. And people say, though I don't know if it's true, that he kept writing, I don't have time in the margin of his papers, because he didn't have the time to put his mathematics on paper before he died. So anyway, but he founded this massive area called group theory. Okay, so maybe I should stop here for a minute and ask if there's any questions.
I was just going to say that the duel wasn't over maths, apparently, John, but I think there's a rumour that it's over a woman, but that's slightly disputed as well, because Galois was incredibly politically active at the time in France. You can imagine that there was a lot of politics in France in the 19th century, and he's one of my favourite examples of a mathematician who doesn't fit the stereotype. He was young, he was incredibly passionate, so passionate that not only did he he was willing to stand up for his beliefs, and indeed ended up dying in a duel. I think it was in his 20s when he died, I think. So yeah, so he's one of my favourite examples of a creative and passionate, brilliant mathematician.
Okay, well, nobody's asked a question about the groups, so I'm going to move on. So far we've been looking at shapes, well, two shapes, a square and a triangle, and their symmetries. And now, obviously, you can also make patterns that cover the whole plane, like these three. So the first one is just made up of triangles, second is squares, and the third is hexagons. And in these patterns, you can also see that there's one other type of symmetry that we haven't come across yet, which is a translation. So a translation would be picking up a pattern, like the square pattern here, shifting it along in any direction, for example, two squares along here, horizontally or maybe up vertically, and putting the pattern down again. And in the case of the square here, the pattern would look exactly the same. So this action, this translating, picking it up, shifting it along, putting it down, is also a symmetry. And in this here, the triangle picture is similar. You can pick it up, shift it along until you place this white triangle directly over this one and put it down again, and what you see looks exactly the same. Obviously, you have to imagine the pattern to continue indefinitely, not just to be in this little square. So basically, what we've seen is that if you think of 2 dimensions, we can have rotational symmetry, reflection symmetries, which are like mirror symmetries, and translation symmetries. And to understand the symmetries of an object, whether it's a pattern or just a finger shape like a triangle, we can just write down a table that shows us how exactly all these symmetries interact. And that table would represent what mathematicians call a group. Okay, so just to stay on the theme of tiling, so these 3 patterns here is what we call tilings, because they're made up of individual tiles that are put together. So here's 3 beautiful examples from the Alhambra in Granada in southern Spain, which has a lot of really, really beautiful tiling. Obviously, in this case, we ignore the colors because, for example, the middle square pattern here, if you picked that up and shifted it along, the colors wouldn't exactly match, but the general, the grid underlying these patterns are very, very symmetrical. And you can see in this one you have a rotational symmetry. You could turn this around and make the shape look exactly the same, ignoring the colors. So these kind of 2-dimensional patterns, symmetric patterns, are incredibly visually appealing, and they've been used in art for centuries and millennia. Okay, so that's symmetry in a visual sense. We've thought about it in terms of shapes and patterns and so on. But what makes this mathematical understanding of symmetry so important is that we can apply to situations where we can't actually see the symmetries, where they're not visual. And that might sound like a really strange thing because we normally only think of symmetries in terms of something we can see. However, here we've got an example on my next slide that it's not all about shapes. So I'm going to give you an example of a situation where symmetry also comes into play. So imagine that you're running a restaurant, okay? And imagine that you have one chef cooking, here she is. You got 2 waiters, and you got 2 kitchen porters, okay? And you're the boss. So your job is to make the restaurant run smoothly. So you have to think about how to best allocate your staff. Now, both of the waiters can do exactly the same things. They're equally well qualified. So you might as well interchange them, okay? So you could say to one of them, well, rather than you serving table 5 and you serving table 4, why don't you switch tables? And that wouldn't really represent a problem. And the same is goes for the 2 kitchen porters. If one of them is washing the dishes and the other one is scrubbing the vegetables, you can tell them, well, just swap jobs, because they both know how to do both jobs, so that's fine. Okay? However, you couldn't really swap the chef with anybody else, because she's the only one who knows how to cook properly, and she may not be very good at waiting tables. Okay? So basically, the problem of how do I allocate staff so that my restaurant runs well is symmetric under a permutation of staff that switches the waiters or the kitchen porters. And what I mean by permutation is simply switching people around, okay? So you can do any switching of people that switches either the 2 waiters and or the 2 kitchen porters. That will be fine, your restaurant will still run, but you cannot switch people that puts the chef into a different position, okay? So the problem of running your restaurant is symmetric under any switching of people that switches either the waiters or the kitchen porters, okay? So if you imagine that you're running a massive operation, not involving just 5 people, but hundreds of people or thousands, doing different complicated jobs, maybe distributed throughout the world, then this understanding of symmetry, of how you can switch people around, is incredibly helpful to solving these kind of optimizational organizational problems. So that's one example where an understanding of symmetry, of doing a transformation that leaves something unchanged, is incredibly important. And another area where it is very, very important is in physics. Now, the example I was going to talk about is a magnet. A magnet is a lump of iron, for example, and it's actually only magnetic below a certain temperature called the Curie temperature, which is about 770 degrees Celsius. If you heat it up above that, it will lose its magnetism. And the reason for that is that if you imagine the lump of iron as made up of lots of little atoms that sit together in an array, as we've illustrated here, now each of these little atoms will itself behave like a tiny little bar magnet with 2 poles, one here and one here. So each of them will have its own tiny, tiny little magnetic field. Now what is happening is when the lump of iron is above the Curie temperature, above 770 degrees Celsius, there are so many thermal fluctuations that these little bar magnets, the little individual atoms, keep flipping around. They keep flipping their magnetic fields from one direction into the other. So the overall effect is that their little magnetic fields cancel each other out, because it's so random that on average they cancel each other out. And that means that there is no macroscopic magnetic field. So the lump of iron itself has no magnetic field because all the little tiny magnetic fields cancel each other out. Now once the temperature goes below the Curie temperature, all this jostling stops and the little atoms align their magnetic fields. And that is what causes the big macroscopic magnetic fields, because they're all now pointing in the same direction, all the little magnetic fields, and they add up to make a big magnetic field. So the whole lump of iron is now a magnet. Okay? Now what does that have to do with symmetry? Well, you need to think a bit carefully here, but basically this situation, the situation where all the atoms are pointing in random directions, in terms of magnetism, this situation is symmetric. Because you can flip directions around, you can turn the lump of iron any way you want, and it doesn't make a difference. It leaves the magnetism unchanged. So we talked about symmetry as an operation that leaves something unchanged. Well, in this case, turning the iron leaves the magnetic field or the absent magnetic field completely unchanged. So this is a symmetric situation. And once the lump of iron cools down, the symmetry is broken. This is now no longer a symmetrical situation because this direction, like the two directions this way and that way, are very different. They define a magnetic field. You just can't turn it around. If you turn the iron around, you turn the magnetic field. Okay? So this is an example of what physicists call symmetry breaking. And symmetry breaking is a very important concept in physics because it is thought that, that basically the whole universe, when it first got started, underwent a massive event of symmetry breaking, which is to do with the Higgs boson, actually, that got discovered recently. And it's that symmetry breaking that basically caused all the mass in the universe to come into existence, including ourselves. So these two examples basically show you that there can be situations where an understanding of symmetry is important that are not just visual. And that's why the mathematical area of group theory, which is looking at these patterns of symmetries and how they can interact, is so incredibly not only mathematically beautiful, but also useful and important in many, many areas of life. So I think I've come to the end of this part. I think I'm going to hand over to Rachel now, who's going to talk to you about some examples of asymmetry.
Okay, so just to finish up the presentation, we've talked a lot about the importance of symmetry, but what is quite exciting and interesting is that asymmetry is fundamentally important in our lives too. And to get an idea of the importance of asymmetry, you just have to look at your hands. So if you look at your left hand and your right hand, if you just look at one of your hands, just your left hand, it's fundamentally asymmetric in that if the only way you can't turn it or flip it to get into your right hand, the only way you can turn your left hand into your right hand is using a reflection. So fundamentally, your hand is an asymmetric object. It can't be spun. If you reflected it, it's fundamentally a different thing. You know that your left hand and your right hand are fundamentally different because if you have a left-handed glove and you try and put it on your right hand, it does not fit. So unless it's a knitty woolen one. But most gloves, you can't fit them on a left-handed glove on your right hand. So why this is interesting, apart from when you're needing to purchase gloves or find a matching pair of gloves, is that this is incredibly important in chemistry and particularly in biological and organic chemistry. So chemists use group theory to analyze the symmetries of structures and behaviors of molecules. And they do this by things like crystallography and looking at the resulting patterns and looking at the symmetry groups of those patterns to understand the shapes and therefore the behaviors of a molecule. So in a lot of inorganic molecules like water, they're highly symmetric, but a lot of biological molecules, I think actually it's the majority of biological molecules, they're fundamentally asymmetric, and so much so that they call them left-handed or right-handed. And what this is usually called is it's called chiral. So chiral is something where you have a left-handed version and a right-handed version that can only be transformed one into the other by reflection. You can't move or turn a left-handed molecule into a right-handed molecule. The only way you can do it is through a reflection. There's, again, lots of questions about why this happens. Really fundamental molecules like DNA are chiral. And what's really interesting is in the natural world, chiral molecules usually only occur in one version. So they either only occur in the left-handed version or in the right-handed version, but not both. And the reason I think this is because like your left hand fits into a left-handed glove, a lot of biological molecules require particular proteins to work on them. And if you had to make both left-handed proteins and right-handed proteins, it would be a lot more tiring, take a lot more energy of that biological system to create both. So that's one of the reasons I think why in nature, mostly you produce one kind of that molecule. You either produce the left-handed or the right-handed version. But what's interesting is if you construct these molecules in a lab situation, you usually produce both. It's not something that happens but you can't often select only to produce the left-handed or right-handed versions. So, because if you're trying to interact with the biological world, the natural world, that's going to have quite a fundamental impact, because the way a left-handed molecule and a right-handed molecule interact with other biological systems is going to have quite different behaviours. And there's quite a sort of sad example of this is that I'm not sure if some of you have heard of a treatment called thalidomide that was used to treat morning sickness in the 60s. And thalidomide, like many biological molecules, is chiral. And in the lab, they produce both left-handed and right-handed versions. And what they think happened is when one of these interacted with the human biological system, it produced no side effects. But when the other handed version interacted with the human biological system, it produced these terrible side effects that thalidomide had. So it's a really sort of sad example of the impact of chirality in sort of biological systems. So it's interesting that both symmetry is vital in our understanding of the world. It is key to our understanding of sort of aesthetic beauty, but it's also used for lots of other reasons. You can have, we use it for understanding geometry and shapes, but we also use it, as Marianne said, for understanding optimization problems of organizations. It's fundamental in understanding physics. It's used as part of chemistry and other areas of science. And that mathematical appreciation, that technique called group theory, is the way that all of these areas use to understand and interact with symmetries. So I guess the sort of next time you look at yourself in the mirror, or you appreciate a beautiful part of nature, or you try and fit your hand into a glove, you hopefully will remember that the beauty of the symmetry that you're witnessing is far more than just something that you're seeing on the surface. It's far more than a visual thing, and actually it's a fundamental mathematical fact of life. Okay, I think that's about the end of our presentation. I'm not sure if there were any questions that came up for anyone during that.
I didn't see questions in the board, but and John did need to go. But Mark, do you have any questions? And we did have someone join us listed as O'Prior number 2. So I don't know if you have some questions. You can type them in the board, or if you have a headset, you can talk. I heard you at the beginning. You have to keep the talk button down to so we can hear. Well, we're not hearing. Can you type your question in? Oh, there we are. Oh, yes, it does take a little time to get used to it. Go ahead and press the talk button. Once you see the blue microphone up there, you can just keep.
What do you think is more important for beauty, phi or symmetry?
Rachel or Marianne?
For me personally, I think, so what I think, O'Prior, sorry if that's a strange thing to call you, what I think you were asking was, were you saying phi or pi?
Oh, he said phi, or I guess PHI. Somebody's talking about the golden ratio.
Oh, sorry. So do you mean the golden ratio by phi? Because I mean there is a lot of beautiful symmetry in the golden ratio. That is there's a lot of beautiful connections. So I don't think I can really say which one of the two is more important. I suppose symmetry is the more fundamental concept, whereas phi is a number that encodes a certain amount of symmetry in the world.
Yeah, great questions. Very interesting. Just, I mean, I guess I see symmetry as the having a lot more complexity and with the mathematics that's involved, as you explained in your talk. But certainly, the golden ratio is fascinating in terms of how it appears in nature. Any other questions or comments? I'm actually going to end the recording now, but stay on. We can continue. Thank you very much. I'll end the recording with a big